Hey everyone, in this video we're going to be going through a combined source and vortex panel method. If you watched my previous video on the vortex panel method, you saw that it worked well for some airfoils where you'd get good pressure coefficient vectors on the surface of the airfoil and you'd get a good lift coefficient, but for other airfoils it seemed to blow up, and it was also very dependent on the number of panels that you used and where you put the panels. So in this video we're going to go through a more robust formulation where we combine both the source and vortex panel method. So the way we're going to start is the way we started for both the source and vortex panel method derivations. We're going to write the expression for the normal velocity on panel I, and we're going to have three terms in this. The first term is the uniform flow. The second term are the source panels, each with constant strength but can vary from panel to panel. That's the same as the source panel method that we did. And then finally, term three are going to be vortex panels, each with a constant strength, and this is where it's different. They're not going to vary from panel to panel. So over the entire airfoil, each of the panels has an associated source strength that's constant over that panel but can change from panel to panel. And with each of those panels there's going to be a vortex, but the value of the vortex strength, gamma, will be the same on every single panel. So down at the bottom we write the equation for the normal velocity, Vn, on the ith panel. First term is the uniform flow term, and the second term here you can see is the source panel term where we have lambda j because the source strength is changing for every panel. And then the third term here looks similar to the vortex panel except that we don't have gamma j, we just have a single gamma because it's constant over the entire airfoil. Now we're simply taking the equation from the previous whiteboard and we're replacing the integral terms by their geometric integral variables that I've derived in a bunch of other videos, and these are going to be the same geometric integral variables as those other videos, so we don't need to change or rederive any of those or change those functions in the code. So we have the normal velocity on the ith panel is equal to the uniform flow term. Now we have the source panel term where we have iij because that's the normal velocity geometric integral, and then we have here the vortex panel term where we have kij, which is the normal velocity geometric integral. Now we just need to see what happens when j is equal to I when we're going through these summations here. So for the source panel term here, we have when j is equal to I, this whole term goes to lambda I over 2. And then for the vortex panel term, this whole term when j is equal to I goes to 0. So we can simply just update this equation as shown down here. Again, uniform flow term. This is the source panel term when j is equal to I, so we just put in lambda I over 2. This is the same summation as above. Now we're just saying when j is not equal to I. This is the same summation as above. Again, just saying when j is not equal to I. I've just rewritten that equation up at the top of the whiteboard here, and now we're just going to multiply all the terms by 2 pi, as we've done in all of the derivations, and we're going to move the knowns to the right-hand side. So that's why we have pi lambda I, because that's 2 pi times this term here. Then we have the source panel term, which is this, and the 2 pi is gone from the denominator, so we just have the lambda j iij. Then we have minus gamma. I can take the gamma out of the summation because it's a constant, and we just are left with kij, the negatives out here, and there's no more 2 pi because we multiplied by 2 pi, and then this term was subtracted from both sides. We have minus v infinity times 2 pi cosine of beta I. Now we're going to write the equations out for our familiar 3-panel geometry that we've used in all the other videos. You can see over here we have 3 panels, panel 1, panel 2, panel 3. Each of the panels has an associated source strength, lambda 1, lambda 2, lambda 3, and each of them also has an associated vortex strength, but this is the same for all the panels, so it's always going to be gamma, gamma, and gamma. And now we'll just expand the equation up here out for one of the panels, so I'm just going to go over panel I is equal to 1, and that's this equation here. So we're going to start here. We have pi times lambda 1, that's the first term. Then we move on to the summation, and we start with j is equal to 1, but that means that j is equal to I, so we skip that one. We have j is equal to 2, so we have lambda 2 I 1 2. Then we go to j is equal to 3, and we have lambda 3 I 1 3. Then we move to this term. Again, skip j is equal to 1 because j is equal to I in that case, so we have the gamma out front, and then we have parentheses for the summation term here, so we have j is equal to 2, so we have k1 2, and then j is equal to 3, k1 3. On the right hand side we just have this term with beta 1 plugged in, and it follows the same way for the other two equations. So in the system of equations down here, I've just rewritten the unknown variables in red and left all the known variables in blue. And so what we can do is then write these equations in matrix form, and that's what I've done up here. So we're just taking the coefficients of the unknown variables and putting them into the appropriate rows. And so we have pi I12, I13 in the top, and then we have minus this term up here, and that kind of makes up the A matrix. And then in the X array, we have all the unknowns. We have lambda 1, lambda 2, lambda 3, and gamma, that's here. And in the B array, we just have the right-hand side. Now looking at this matrix system, you might see that we have a problem. We have n unknowns, in this case 4, and we have n minus 1 equations, 3 equations. And this is a problem right now because we can't solve this system yet. It was not a problem technically in the just the vortex panel method because we had n equations and n unknowns, all of the vortex strengths on each of the panels. Now we still need to enforce the Kutta condition, so in the old vortex panel method, we actually had to replace one of the equations in the matrix so that we didn't have a system that had n plus 1 equations for n unknowns. And so in this case, though, you can see that we're missing one equation, and so we can actually just apply the Kutta condition equation as this last equation. In the other vortex panel method, the way that we applied the Kutta condition was by stipulating that the vorticity at the trailing edge was equal to 0, which gave the equation that the sum of the first panel gamma and the last panel gamma was equal to 0. Now, if you tried to apply that in this case, because we're only using a single vortex strength for every single panel, you'll note that that will give the result that gamma has to equal 0. So that's not going to work. We're going to need a different Kutta condition. So to get the equation for the Kutta condition that we're going to use, let's look at the first and last panel. So here we have the first panel, and up here we have the last panel, or the nth panel, and you can see the airfoil goes around this way. That's the convention that we've chosen for all of our derivations. I've also drawn the tangential vector for each of the panels. You can see T1 goes this way, Tn goes this way. And so we'll approximate the Kutta condition by setting the first and last panel velocities equal to each other. And that's expressed in equation form here as the tangential velocity of the nth panel is equal to the negative tangential velocity of the first panel. The reason there's a negative here is because we want the first panel's velocity to be going in the opposite direction of the positive tangential vector. And so we can then just move this term to the other side, and we get the equation Vtn plus Vt1 is equal to 0. That is our new Kutta condition equation. So you might see right now that this Kutta condition equation is going to be much more involved than the simple vortex panel method Kutta condition equation that we used. For that one, all you had to do was substitute one of the equations in the matrix system with just 1, 0, 0, 0, 0, 0, 1, and that took care of the Kutta condition. Here we actually have to solve for both of these velocities, the tangential velocities, and then find that full equation and then add that into the last equation of the matrix system. Okay, so let's just jump into writing these two expressions. So we're going to start with the tangential velocity on the first panel. This is from the uniform flow term, sine, because we're doing the tangential velocity. We're putting in beta 1 because this is for the first panel. Then we have the summation for the source panel terms, and we're explicitly saying that we're going from j is equal to 2 to n because we're on the first panel, so I'm just going to write that explicitly. We have the lambda j, and then we have j1j. We're using the j, the capital J variable, because this is the tangential velocity geometric integral. Then skip this term, go over to here. Now we have minus the summation for the vortex panels, and so we're doing gamma times L1j over 2 pi, and again, L is the geometric integral for the tangential velocity from the vortex panel method, again going explicitly from j is equal to 2 to n because we're on the first panel. This term right here comes from the j is equal to 1 term from the vortex term here, so we have 1/2 times gamma 1. This is a little confusing because from the previous whiteboards, we had the normal velocity where this term came from the source panel. It just flips to being from the vortex term when you're talking about the orthogonal velocity component. So for the normal velocity, the j is equal to I term comes from the source panel. From the tangential velocity, the j is equal to I term comes from the vortex term, and that's why that's here. Now we can talk about the tangential velocity on the nth panel in the same way. So here we have the uniform flow term, again sine because of the tangential velocity, beta n explicitly. Here we have the summation term from the source panels, and here we're going from j is equal to 1 to n minus 1 because we don't want to solve for it on the nth panel. Then we have lambda j, j n j over 2 pi. This is from the j is equal to I term from the vortex terms. We have 1/2 gamma n minus the summation from the vortex panels. Again, j is equal to 1 to n minus 1 gamma L n j over 2 pi. Now we're just going to add both expressions from the previous whiteboard, and we're going to set it equal to 0, and that will be our Kutta condition equation. Also note that gamma 1 is equal to gamma n is equal to just gamma because it's constant over the entire airfoil. So here we have the first panel equation, VT1, and then here we have the the last panel equation, that's VTN, and that's equal to 0. Okay, now we're going to do 3 steps in one. We're going to group like terms near each other. We're going to move the knowns to the right-hand side, and we're going to multiply everything by 2 pi. So first things first, for these 2 terms here, I'm just taking the j term. So I'm taking this guy, and I'm taking this guy. That's this. Then I'm going to take the L terms. So here I'm taking this guy, and then I'm going to take the j is equal to I gamma term. So that's this and this. Those are here. And then we're going to move this term and this term to the other side, which is why we have the negatives. And note that now, since we've also multiplied by 2 pi, all the 2 pi's in the denominators here are gone. This term and this term are equal to 2 pi over 2 gamma for both of them. And then in each of these terms, we have a 2 pi. Okay, now this equation right here is actually fine. And I'm actually going to go back to it when I'm putting the Kutta condition equation into the matrix system. However, for coding, we're going to make 2 last steps because it'll be easier for putting it into the code. So the reason we grouped like terms together in this equation is to make it easier for this next step where we're going to further group the terms. I'll get back to the colored stuff in a second. So first we're going to take these 2 terms here and we're going to combine them. So we have the summation from j is equal to 1 to n, I'll get back to this in a second, of lambda j, that's in both of them, times the quantity j1j plus jnj. Then we have this term here, we have plus gamma. We can take gamma out of the summation because it's constant. And then we have in here, so we're going from j is equal to 1 to n again, minus quantity L1j plus Lnj. These terms here sum together, and because it ends up being pi gamma plus pi gamma, we get plus 2 pi gamma. And then on the right-hand side, we have the common term in both of these is negative v infinity 2 pi, and then we just have sine beta 1 plus sine beta n. Okay, so back to these color terms for a second. So you'll note that I'm doing the summation from j is equal to 1 to n, and so these are showing that for the j1j and the L1j terms, they're only supposed to be included in the summation when j does not equal 1, and for the jnj and Lnj, they're included in the summation as long as j does not equal n. This is only to keep things straight on the whiteboard, but in code, the way that you can take care of this is to just set the on diagonals for both the j and the L matrix as zeros. That way you can sum from j is equal to 1 to j is equal to n and not have to worry about which indices you're excluding because they're going to automatically be 0 because those values of j and L, when j is equal to 1 or j is equal to n, they're already 0. Now we'll just do one final grouping, again just for the code. So this whole equation is the same except for this term right here, and that's because you can see there's a gamma right here, so we can pull this 2 pi into this whole term right here. So we have gamma outside, then we have the full brackets around this, and then we have, or the braces, then we have the square brackets around the summation term, just this term right here, and then we have plus 2 pi. This is the equation that I'll be referencing in my code, and this is how you'll kind of see it coded up, is based off of this final form. So like I mentioned before, we're going to go back to an earlier form of the equation because it'll be easier to put it into the matrix form, and so that's what you're seeing up here. We've already gone over this equation. Now, to put it into the final matrix form for the 3-panel system, I'm going to expand this equation for the 3-panel system, and that's what you're seeing down here. So these 2 terms here come from this first summation, the next 2 come from the next summation, these 2 come from this summation, these 2 come from this summation, then we have plus 2 pi gamma here, and then we have the right-hand side. Now the last step in this process is just to add this equation into the matrix form. This is the same as you saw a little while ago. The first 3 rows are the same, and we just had to fill in this last row, and that's the Kutta condition equation. And so we're just going to see where these variables are in this equation and add those terms down here. So the first one, we need to find lambda 1 for this first position. Lambda 1 only shows up here, And so we get J31. Then we look for lambda 2, lambda 2, lambda 2. So we have J12 plus J32. Then we look for lambda 3. Lambda 3 is here. There's only one of them. So we get J13. Then for the gamma values, we have this, 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 and this. So I just factor out the negative from all 4 of these, and we just add them all. So that's why we have L12 plus L13 plus L31 plus L32. That's taking care of all of these. And then we have plus 2 pi, and that's times gamma. And then we have just the full right-hand side on the right-hand side. And to solve for the unknowns in the X array, we can just use a normal solver in MATLAB or Python, and we get lambda 1, lambda 2, lambda 3, and gamma. Okay, so that's all there is to it. You just have to solve this matrix system of equations. The coding of this is a little bit trickier than the other methods, but I go through that in my next video, so stay tuned for that, and thanks for watching.